तो आज हम करेंगे कुछ यूजफुल रिजल्ट्स कॉन्वेक्सिटी और कनकेविटी के। अगर हमें पता है कि दो फंक्शंस कन्वेक्स या कनकेव हैं, तो उनके मिक्स्ड कॉम्बिनेशंस या उनके नेगेटिव्स का क्या होगा, ये हम आज देखने वाले हैं. So we have already started convex and concave functions defined over convex sets. That is very important. The domain of the functions has to be a convex set, and we all know the reasons why. Now let's start with today's class. So we would be discussing this theorem. So let f and g be functions defined over a convex set in Rn. So we are going to have a general discussion over functions over Rn. What do you mean by Rn? Rn means the n-dimensional space. That means my convex set, okay? So my convex set, which is the domain of my convex and concave functions, it is going to be a subset of Rn. And how does an element look like in Rn? It is going to have n components, okay? And all these components belong to the set of real numbers. Okay, so let's state these results. Let f and g be functions defined over a convex set S in Rn. Then if f and g are concave and a greater than or equal to 0, b greater than or equal to 0, then a if f plus bg is concave. So it is saying that any linear combination of concave functions, any linear combination of concave functions is a concave function. Okay, provided the linears are non-negative. We don't want to have negative linear combinations. We want A and B to be non-negative. They can be 0, but they cannot be negative. Okay, so let us see how this result is obtained using the concavity of f and g. So we are assuming that f and g are two concave functions over a convex set S. So I want to prove that AF plus BG is concave, okay, where A is greater than or equal to 0, B is greater than or equal to 0. So if we look at the convex combination of two numbers in the domain, so let us consider x and x naught in the domain, and let us take lambda in 0, 1, and let us look at their convex combination, which is 1 minus x plus lambda x naught. This is also in S by the virtue of S being a convex set. Then let us look at AF plus BG and take the functional value at this convex combination. Okay, now by the virtue of functions, this will be distributed. So I'll have A and f of 1 minus lambda x. So this is equal to this plus lambda x naught plus b g of 1 minus lambda x plus lambda x naught. This is just by the definition of functions. So now we know that f and g are concave. Since f and g are concave, we are going to have f1 minus lambda x plus lambda x naught greater than or equal to 1 minus lambda f of x plus lambda f of x naught. And this is going to happen for g also. And therefore, as A and B are greater than or equal to 0, the inequality will be preserved. So right now we have equality sign, and now we have greater than or equal to sign for f and g. And because A and B are non-negative, the inequality will be preserved. What does it mean? So now this particular expression will be greater than or equal to A 1 minus lambda f of x plus lambda f of x naught plus A 1 minus lambda g of x plus lambda g of x naught. Now you just have to combine these in terms of AF and G. So now you are going to have 1 minus lambda, take common. You will have AF, okay, plus BG at X plus lambda times AF plus BG at X naught. You can see that AF, then this is BG, okay, BG and of X, and 1 minus lambda is common. When you take lambda to be common, you will have AF plus BG, and that is evaluated at x naught. So you started with a convex combination of x and x naught in the set S, evaluated it for the function AF plus BG, and you notice that for this function, we are getting the inequality greater than or equal to, and I was able to split the function as 1 minus lambda, the functional value at x, plus lambda, the functional value at x naught, and where the function was AF plus BG. And therefore, AF plus BG will turn out to be a concave function. This completes the proof. And now you can remember this for your application part. You have two concave functions. You can use any positive linear combination of those two concave functions to create another concave function. Okay, and the same will hold for convex functions also. Any non-negative linear combination of convex functions will also be convex. So the part B of the theorem can be attempted by all of you as an exercise, and that will give you a lot of confidence in how to go about the proofs. Okay, now let us look at part C. Part C says if fx is concave and fu is concave and increasing, then ux is equal to f of fx is concave. Okay, so I am looking at again x and x naught in the domain. Okay, And now let's evaluate u at their convex combination 1 minus lambda x plus lambda x naught, where lambda belongs to 0, 1. Okay. Now my u is a composition of capital F and small f. So this is capital F, and then you have small f and 1 minus lambda x plus lambda x naught. Now I will be doing something which should not be very difficult to understand. We know that capital F is an increasing function that is given to you. Okay, and small fx is concave. Okay, so what does it mean? It means that f of 1 minus lambda x plus lambda x naught should be greater than or equal to 1 minus lambda f of x plus lambda times f of x naught. This is by concavity. अब आपको पता है कि अगर कोई फंक्शन इंक्रीजिंग है तो क्या होता है, x1 greater than or equal to x2 should imply capital fx1 greater than or equal to capital fx2, because capital F is an increasing function. So now this is my x1 and this is my x2. So this would imply that capital f1 minus lambda x plus lambda x naught should be greater than or equal to capital F 1 minus lambda fx plus lambda f of x naught. This is the most important part of this proof. And therefore now in my proof, I can replace this equality by inequality, and I can write capital F 1 minus lambda f of x plus lambda f of x naught. I will not be able to do this unless I'm given that f small f is a concave function. I could do it only because small f is a concave function and capital F is an increasing function. Okay, now I'm given that capital F. Now because capital F is concave, okay, function. So now what do you think should be happening? So now this is again a convex combination of small fx and small fx naught. So this should be now greater than or equal to 1 minus lambda capital F of small fx plus lambda capital F of small of x naught. Now this is by the concavity of capital F. Okay, capital F is concave as well as increasing. So now this is nothing but if you see, this particular thing is 1 minus lambda u of x plus lambda u of x naught, and we are done. We have proved that capital U is a concave function. This is a wonderful result. So always remember that if you have a small f which is a concave and a capital F which is concave and increasing, then if you take the composition of capital F with small f, of course capital F has to be outside, then the resulting composition of functions is going to be a concave functions. Okay. All right. So similarly, you can attempt D, capital D, small d, fx is convex and fu is convex in increasing, then this is convex. It goes exactly like this, and it can be taken as a practice problem by you people to gain more confidence in proving things, as I said earlier. All right. Now let's start E. If small f and g are concave, then hx defined by minimum of fx and gx is concave. So again, let us look at x and x naught in the convex set S, and let us try to evaluate h over a convex combination of x and x naught. Okay, this is minimum of f 1 minus lambda x plus lambda x naught, comma g 1 minus lambda x, okay, plus lambda x naught. All right. So the minimum of f and g will be either f or g. So suppose minimum is f, then this is going to be f of 1 minus lambda x plus lambda x naught. Now small f is a concave function, so this is greater than or equal to 1 minus lambda f of x plus lambda f of x naught, which is equal to 1 minus lambda minimum of fx and gx, because here minimum is f, plus lambda times minimum of f at x naught and g at x naught, and which is equal to 1 minus lambda h of x plus lambda h of x naught, and therefore we have proved that h is a concave function. So minimum of two concave function is a concave function, and maximum of two convex function is a convex function. Again, this can be attempted as an exercise. And now you people can see that how convex and concave function satisfy some properties beautifully. So you can actually, play around with convex and concave function. There are many functions. For example, e raised to the power x is a convex function. Okay. And you can take another convex function and you can look at a positive linear combination, try to draw the graph and see what is happening. So this way you can create utility functions. Okay. Knowing that you have some basic convex or concave utility functions. Thank you, everyone. I hope you understood the class.